the videos. So this one will go up after I create it as well. I think I'm up to date with posting all of the lecture material. Let me know if something's missing, okay, if you need something. There is a question about the exam, and so I will actually find some example problems that are from previous exams and compile them in something to post for you so you have something to practice. Specifically from this last material, we haven't had really a homework for the differential equations, but just like everything else, so far you've seen kind of like certain motions in place. We describe a method, we motivate how to do it. You need to know how to do it by hand, a couple of iterations, and you also need to know how to program it. And the assignment I give you will be, well, it will be some ODE, and I'll tell you, well, using this and this method, please either do it by hand for a couple of iterations and calculate the error, or program it. So that kind of dynamic is going on, so because that's basically what we're learning here. We're using programming as a tool to help us solve these. So you need to know mechanics of that. But there is also understanding how the method works, and you do a couple of iterations. Yes?
Most professors put an emphasis on the final and the final topics we learned in the class, so you're going to do that also.
Oh, so what will actually happen, again, it's not going to be, the final will not be 9 till 12, it's not going to be a 3-hour final. We've tested enough already. So it's going to be maybe not 5, but 6 problems. So 5 or 6 problems again, so maybe a little longer than the, so up to 2 hours at most.
But is it going to have emphasis on these last topics we're learning?
Yes, so basically we will learn, so what we haven't had on the exam starts with curve fitting. Right? So you will have one larger question on curve fitting, one on differential equations, and there will be a very short introduction to numerical integration this last period. So basically, those are going to be 3 questions. And then the reminder will be pulled out from the previous material. Does that answer? So yes, some review. Again, in terms of programming, I'm like lecture, well, I'm testing programming and everything that you do now. So I don't need, but I can have couple of shorter questions. How do you create an array? How do you do this? Like the ones we had at the beginning. So essentially, yes, so each of the topics that we haven't had on exam 1 and 2 will be 1 question. And then the rest will be a review of the previous. All right. So let's continue with ordinary differential equations. So we have introduced 2 methods so far. Let me quickly open slides so we briefly review them. And I was just about to finish yes, office hours are right after this.
Is the lecture going to be available online later on?
Yeah.
So that, because I missed the part.
I'm
of
up
the
to
exam.
date, so all of them.
Thank you. So I could.
Oh, yes,
really
this is all
interested
being
about the
recorded,
exam.
yes, so you can hear that.
Yeah, so I can hear that. So it's recording right now. That's great.
Okay. Okay, so we have programmed Euler's method last time. So this is a very simple numerical method for solving ordinary differential equations that essentially does the following. So every time we are solving, we need to have a starting point. It's an initial value problem. And we are solving equation of the form y prime of x or dy dx. So derivative of function y is equal to some function of both x that y depends on and y itself. Okay? So that could be quite complicated looking. And then if it's complicated looking, it's difficult to integrate and actually solve that ordinary differential equation by hand. So we are providing here with the numerical options of how to solve it. Just like any numerical solution, you don't get the actual function y of x is equal to something, what you get is actually point-wise solutions. So you discretize your space, you give yourself a finite number of points on some interval, starting with the point where you actually have a value, and then you iterate. And iterations, the way iteration says here is, okay, using the point you have, so here I'm labeling it xi, yi. Using that point, step forward as follows. Evaluate the derivative of y at that point, which you actually have given here. That's f of xy. So the derivative at this point, or the slope, is f of xi yi. Okay, so I can evaluate that. I do know f. And then take that, it's basically a linearized version of your function. However complicated function is, you're actually kind of approximating it with a line at that point. And that line, take it for this step h over here. And basically the value here, the predicted value here, is then this previous value yi plus the slope times h. H is your difference between your next step, xi, next point, xi plus 1 minus xi. Okay? So this is your h. So basically then that value is yi plus 1 is yi plus f of xi yi times h. And that's what we programmed. It's actually a simple loop that literally has this as a one-liner in there. And the rest is just like preparing to get into this loop. And your result is then an array of values x and array of values y. Okay, great. So we did that, and basically when I compare for different steps h, this is how it looks like. So as h gets smaller, I get closer and closer to analytical solution. In this case, the example was simple enough, so we can integrate and actually compare with analytical solution. Now, the next method, all of the other methods are figuring out that slope, f of xi, yi, the slope that I took. They're basically improving that. So in this case, f of xi, yi, the one idea to improve is to essentially take this slope at this point here, and then slope at this point here, and average them. And that's what we started solving. So basically, I take this second point is where Euler method would put a prediction. I take that point and I evaluate slope there as well, and then I average the one I had and that one. Okay. So let's see how does that work, and does that work any better? So basically copied my is this my Heun method? Yes. So I have copied my function Euler method and I just renamed it as Heun. Heun is a German name, which is why I'm saying it in a funny way. So essentially, I'm still having the same inputs as I did in my Euler method. I discretized my space. I reserve space or memory for my results, y. And I set the initial value of y. This is very important, so we start on the right, using correct value. And then for all of the points that I have, basically starting from 0 to n minus 1, I don't need the last one because I'm always kind of doing one step ahead in this formula. So basically I find this, what I now call intermediate point, is basically the point that Euler method would have computed. And I estimate slope as average of my initial slope that I used for Euler method plus slope at this intermediate point. And I divide that by 2, and my next point is then y of I plus the slope.
Can you just roll up to so I can see what you define it as, please?
Define what?
This one.
This is the two pieces that are different from Euler's method are
No.
these three lines.
Heun method.
Heun. Heun. All right. So let's see how it works. So let's actually, what I'm going to plot as I'm gonna go below and test. So basically I'm gonna say XH, YH here is Heun method. And I'm gonna test it for that 0.5 because there the H is 0.5. That's where we're gonna see the improvement, if anywhere. And I'm gonna calculate the analytical solution too, and I'm gonna plot and I'm gonna do some, so I'm gonna do stars for this, blue stars, red, solid, and then I'm gonna put this as a line. So that's my analytical solution. Excellent. So let's just plot this comparison. Whoa. Oh, I did not, I just, yeah, I need to run all of them. Standard problem. I just reopened it. Okay. And then I need to run twice just because. Here we go. So this is my Euler. This is, or Euler. Yeah. So again, Euler and Heun are German. I did study some German for some good 5 years. That said, I'm not conversant in German, but how to say things has stuck with me. My German is on the level of a 5-year-old. I can ask where the toilets are and I can say I'm hungry. That's essentially my level of German. But I still pronounce things when I see them. Okay, so this is where my Euler method was. Pretty good, just for averaging those two slopes. Look how much closer for the same spacing I got. And of course, this would improve as I removed it. But this is where we see the biggest difference, right? Actually, I don't like this plot. I do like lines. I'm going to put lines here as well. So, all right, so I have lines for everything. See? So that's quite an improvement. Yes?
Do you know if the improvement is affected by the step size? Like the amount improved would decrease with smaller step sizes? Does that make sense?
Yeah, so everything decreases. Especially, so let's say if that order of them, if you actually numerically analyze, this one is a first order method, so your error is O of H. Okay? This one is a second order method, but likely O of H squared. Okay? So as H gets smaller, you have O of H squared, which is much faster, and so it's an order faster. So yes, but even here, it's pretty good, right, for such a large step. So this is how I plotted the comparisons. Okay, so I'm going to move on now to something that is super duper order. And I could actually improve this. So this what's called predictor. You could actually do a little loop and try to get that error smaller and smaller, and this would improve even further. Okay. So this intermediate step could be what's called this creating this slope could actually improve multiple times. We're not going to do that. Already this one step was pretty good. Now, technically, I could get even better, even on such a large step. Generally, there's an entire family of methods. And all of these are called so-called Runge-Kutta methods that basically really perfect the trade of finding that good slope. And the way they work is like, okay, I get a number of predictor points, okay, and slopes. So in this Heun's method, we took one slope. My mouse is not following where I'm going. All right. I had that first slope, and then I took that slope, and that got me that intermediate point, and I found a slope there, and I averaged the two. I could technically do a number of such steps, n of them, okay? And not necessarily do an average, but basically do a weighted sum of these slopes, okay? And that can improve. Now, this doesn't, it's not pulled out of the weeds. It's actually done by analyzing Taylor series. We're not going to do that, right? But basically, these points are carefully chosen so they actually eliminate up to certain order of Taylor series elements. And that's how they achieve accuracy. And predictably so, not just in one case, but for most functions. Okay? But for that, you have to have more of these. So I'm going to explain one of them, and I'm going to explain it essentially geometrically. But again, these are not pulled out of the weeds. They're basically, you put things in Taylor series, and you try to get them to eliminate up to 4 orders here in Taylor series. And that's what gives accuracy. So here's how one of these methods would go. I give myself first slope, K1. Okay? That's simply my f of xi, yi, just like in Euler's method. Then I take that slope, okay, for half step h. So this is my point at half step h, and I take where I would get prediction, and I get a slope there, and that's my slope k2. Then I take that k2 also for half step, and that's my slope k3. And then I take this k3 slope for entire step h. And that's my slope for k4. And then the final slope that I actually use is a weighted sum of these 4. So 1/6 of k1, 2/6 of k2, 2/6 of k3, and 1/6 of k4. Okay? That's what's a weighted sum. Sum of these weights is 1. Okay? Okay. Let's see how that works geometrically. So here I am at the spot xi, yi. I take this slope that basically is f of xi, yi. Okay? That's the slope that Euler method would give me. And I take it only half of the way to here. Here, I estimate what my slope would be. It would be f of this point, xi plus 1 half h, and yi plus 1 half k1h. Great. So I take that as a second slope, k2. And that slope, I basically look at what it would be here at the functions, is this. Excellent. So I take now this slope, and I also take it halfway, okay, to this point. And I also find what the slope is using f at this point, and that gives me slope k3, okay? And then I finally take this slope k3. I take it all the way for the entire step h, and I find my final point there. These are all some sort of intermediate points. And I estimate what f of xi plus h and yi plus this third slope times h would be right here. And that's basically coming from this. Great. So those are my 4 slopes. When I do the weighted average, I basically pretty much land on the spot. Let's program that and see that it works. Okay? So basically, you're gonna, it's just calculation of all of these, right? I'm gonna leave this as a slide over here. But what you're gonna do just to program that is take that Heun method that we had. Cut, copy, paste is a beautiful thing in coding. Copy it and create a new one, and we're gonna call this Runge-Kutta. Our inputs are the same. We're just gonna change how we do slope, really. And creating x and y, that's all the same, so that's all reused. The change is here. So here is where I'm going to say my K1 is, for instance, this. Okay? Just like these slides tell me. And then my K2 is this. My K3 is this. My K4 is this. And then finally you have to estimate slope. So this is that weighted sum. And this is your final say on what y should be. So basically just fill this out.
Did we copy the Euler method?
Either of them works. I copied Heun's method. And then you delete that in, you leave that xyi plus 1 is y of I plus slope times h. It's just the slope itself will change. This is called reuse of the code. And that's important thing in coding because you kind of often have to adjust, but there is certain skeleton of the code that can be reused. And there's no need to, if the code works, then you copy the part that works. You don't have to weed out errors, aka debug the parts that work. It is a moment of truth for me. Boom. So it's again all how I estimate this slope. Here it's quite complicated. Just know that somebody actually did a calculation and this can be figured out You just don't have the time to play with that. So one of these days I'll get motivated. I love these. Like figuring out what coefficients to choose. But I like numerical methods, so there. But yeah. That's why I'm here. Okay. But it's a fun exercise, actually. You can design a new method. Did everybody else get this typed in? It's really about typing it in correctly from slides. And this is accuracy, basically. This is what's called fourth order. My results for Runge-Kutta is right on top of the analytical solution, even for H is 0.5. Look at the difference. What do you mean changed?
Well, sorry, the Euler method changed, which is like the graph description. I mean, I know what you have, but.
It's still in the same shape, so I think it's just about
The one.
Okay? Okay or not okay?
No, I can get it.
We've got at least something produced, but not quite up to snuff. You have something?
Well, I didn't know what values to type in. I just need the values for HX.
They're the same as the other ones, so you just basically executed with the same inputs. Ah!
Yeah, sorry. But I got the code, I don't know the value.
Okay, it's 0,
3.5.
H is 0.5,
Oh, 0, 1, 4.
so 0.5, this is what I'm doing. 0.501 is your initial point, and then 4 is up to where you want to go. Anybody has something they want me to look at? Yeah, that's it. See that the green points are right on top of the analytical solution, which is black. Even for this, look how bad the blue line is. So you didn't plot analytical. Oh, so this is Euler. Yeah, your solution should be right on top of analytical solution. Yep. There is your solution right on top of analytical? Alright,
Undefined.
everybody else good? Alright. Okay, so just one.
What's your graph look like?
Look at that.
That's not what mine looks like.
There you go.
When you post the code, because I didn't get.
Yeah, I will post the code.
I didn't get anything either.
So there is a whole set of methods, and if you need practice for your exam, then pick yourself a method and program it. Okay? That's essentially what's going to show up as a problem. I'll give you a problem and then program it. So there is, again, it could go third order methods with 3 slopes. It doesn't really matter. Like, I can give you a formula and you can run with it. Okay, so we have just done this comparison. So one small thing that we can also do is also figure out how to do systems. Okay. Now, systems, I often have 2 things that I'm monitoring, and they're depending on each other. And there's a classical predator-prey model where I have a population of gazelles and a population of lions, and lions eat gazelles. So the number of gazelles depends both on gazelles themselves, and do they have little baby gazelles, and how many, and lions, and whether they, and how many of gazelles do they eat. And populations of lions depends on whether they have food, which is gazelles, as well as do lions have babies, okay, and what is the rate of those. So those are coupled together, and you can find a lot of other examples. Typically, it's not just 2 things. That's when we're lucky. Most of the time, you have 20 things that are depending on each other. But those are the systems that are coupled. So you could be having a function here whose derivative or change depends both on that function, the variable that you're looking at, for instance, time, and that other function that you have to solve for simultaneously. And we can solve these equations as well using similar methods. What we do, okay, so let's say they have dy dx is some function of x, y, and z. Z is this other function. And dz dx is some other function of x, y, and z as well. So those are coupled because y is affecting how z changes, and z is affecting how y changes. That's how they're coupled, right? Just like these populations of lions and gazelles. And you would proceed in the same way, okay? Numerical solution would basically, in the simplest case, if I had Euler's method, I would just do this f1 as my slope, right? But I would solve for them simultaneously. So in this case, I'm solving both for y and z, yes? With Euler's method. So then, if I had Runge-Kutta, I would do the same. It's just I would have a maze of all of these slopes, but because I would have 4 slopes times 2, okay? But it's again working in the same way. So this is how we would solve systems, and you could technically solve for n of them at the same time. Just a moment. I don't know where's this sound. Okay. So that is basically the systems. And there is one trick of how I can actually transform a higher order equation into a system. So essentially, if I had y double prime of x plus 4y is equal to 0, I can call my z a y prime. So I'm looking for both y and y prime as 2 functions at the same time. Okay? And my one equation is simply that my z equals to y prime, right? So which is dy dx. dy dx is equal to z. And my other equation is the actual equation that I can derive from here. And that's how I can actually solve for systems. So basically, in this case, my y prime or dy dx is equal to z. That's my function f2. And if I had z prime, which is y double prime, that's from this equation equals to minus 4y, and that's my f1. So I can actually convert a second order equation to two equations that I solve for simultaneously as a coupled system. And then I'm looking both for this y and z, so I'm looking both for y and y prime at the same time using the same code. And of course, do have to have initial conditions here, so y of 0 is given as a 0, and y prime of 0, for instance, is equal to 1. Okay, so I would work with those.
Y with inverted comma mean? Y second?
Derivative.
Y double prime.
Double prime. Okay, so basically this is how you would go for it, and there's like a solution provided on the slide in there if you were actually looking for it. Okay. So basically my dy dt is this function 1, and dz dt is this function 2 that I figure out from algebra. And then you use this, for instance, Euler's method to solve for this Euler's method you would use to solve for that. Okay, so it's just tagging along, moving along to it. All right, I will disappear now. Please fill out the survey, and I will see you on Friday. And don't forget to sign, and then together with those, just give that sign-up sheet to Leah in